So hi everyone. So today it's our great pleasure to have Ruimeng Hu from University of California, Santa Barbara, who is going to talk about convergence of empirical measures, Midfield games, and signatures. So thank you very much, Ruimeng, for accepting the invitation, and well, the floor is yours.
Oh, thank you, Matthew, for the introduction and also for the kind invitation. So really sorry for the delay due to this technicality issue. Today I'm going to present I was planning to present two works. The first part is with my collaborator Jie and Ji Hao from Princeton. The second one was with a student I'm supervising. Due to the delay, let's see if I have enough time to cover both topics. Okay, so let me start with the first one. The first one concerns a question arises in many field. So let's say if you have a distribution mu which has the pith moment on RD space, and then for observations x1 until xn, you are able to construct the empirical distribution, which we denoted by mu bar n, and its number of observations. And then in many scenario, we can see that the distance between the empirical distribution, empirical measure to the target distribution converges to 0 as we observe more and more samples. And then there are some metrics measuring the distance between these two measures. And then the most famous one, or the one that people use mostly, is this Wasserstein metric. Okay, so why people care about this convergence things? So for example, if you try to learn a distribution from finite samples, then you want to know how many samples you need in order to have a close enough, a good enough approximation. Or this can also describe the propagation of chaos of a n-particle system. So if you have an n-particle system, they have interactions, symmetric interactions. Then as the number of particles goes to infinity, then you would be able to see that the law of those population can converge to a distribution which is described by this Moquin laws of stochastic differential equation. Okay, and then from another perspective, if you are concerned about a n-player game where the players are all symmetric, then and the number of the players are large, then you can naturally go for this Midfield game, and then you use the Midfield solution to approximate this n-player game. And this is called the approximate Nash equilibrium, where for the last part, this approximation also is also related to this convergence, or the speed of the convergence. Okay. So then let's take a look about what has been used in the literature. So let's quickly review what is the P-Wasserstein metric. So if we if mu and mu prime, they have the pith moment in the RD space, then we can define the P-Wasserstein metric to be the infimum between all coupling measures between mu and mu prime, and then integrating the integrand is the piece distance between the two vector in RD, and then you are taking the 1/piece root. Okay. And then Wasserstein metric has been widely used in many areas, in particular in optimal transport, where intuitively this is the minimal effort that you are reshaping one pile of sand to another pile. And this is also used in machine learning, for example, in this Wasserstein GAN, and in other like learning graphs using Wasserstein metric. But we usually observe those a potential problem in high dimensional applications, which is known as this curse of dimensionality. So what do I mean by the curse of dimensionality here is if I'm using the P-Wasserstein metric to measure the distance between a empirical measure and the target distribution, and as long as we have enough interoperability of this distribution, then you can always see that the upper bound of this distance is related to the dimension of the probability distribution, the dimension of the underlying space. And in particular, the larger D is, the larger the bound is. Okay, so imagine that if you have a 10-dimensional vector, I mean, if you have a distribution on 10-dimensional space, then this will be n to the power minus 1/10, which is relatively small. So if you want to have a smaller gap between your empirical measure and the target distribution, you want to have many samples, right? So then this motivates us to think about whether we can have a metric. Of course, by prescribing something, can we get the convergence to be free of the dimensionality? Okay, so this is the motivation of the first part. And later on in the later slides, you will see that the answer is yes. And then we do have some criterion for this phi function here. That's our notation. And that is closely related to the function space that are induced by neural networks. Okay, so before talking about the real definition, let's take one step back and then look at another definition which has been widely used in data science. So that is the maximum mean discrepancy. So this is a efficient object to measure the discrepancy between two measures, mu and mu prime, for high dimensional data, and that has been used in like biological data, for example, in this paper in 2006. Okay, so basically they take a class of test function which they denoted by phi, and then they are integrating with respect to of this testing function f with respect to the difference between these two measures. And in particular, for their MMD, for their maximum mean discrepancy, they take the phi to be the unit ball of a reproducing kernel Hilbert space. And the very reason to take phi in this way is they can do a quick evaluation for this integral, the difference of the integral. So for people who didn't have much are not very familiar with the RKHS, basically a space is called RKHS if functions f, if all the functions in a space such that the linear and point evaluation functional mapping exists and is continuous. And one way to construct the RKHS is through a positive kernel function, which maps RD cross RD to R. Okay, and then it is defined in the following way. Okay. So I will try to be quick on this part, but a very common example that people widely seen is the Gaussian kernel, where you have this exponential function. Okay. And when people talk about the kernel method, it's very related to this RKHS. Okay. So then let's see what's common in for these two metric. So if we take the dual representation for the one system metric, then we can also say that this is a supremum over some functions in the class of the integral of this test function with respect to difference between two measures, where now the test function class is all continuous and one Lipschitz functions. Okay, so there's indeed some common structure between the system metric, the one system metric, and the MMD. Okay, so they take they share the same structure, but they choose different test function class. For Wasserstein, we have the one Lipschitz function, and then for the MMD, which we just mentioned, this is the unit ball of the RKHS. Okay, so then our idea is to propose a general concept, which we call the generalized maximum mean discrepancy. And instead of specifying the class of function for this phi, we prescribe three conditions for this phi. And for all the function class that satisfy these three conditions, this can serve as can serve as a function testing function class, and then this will give us a GMMD metric. Okay, so what are the criteria for the phi here? First of all, we want to say that this testing function class is rich enough such that if I am integrating against a measure which give me 0 for all the functions here, then this has to imply that my measure is 0. So we want the some richness of this test function class phi. Okay. And then the second part is the Lipschitz conditions. This guarantees that the integrability of the right-hand side and then the finiteness of this GMMD, basically. And then the third part is the most important thing, which give us an upper bound for the empirical Radmacher complexity. So Radmacher complexity describes the like the richness of the test a class of functions for given data points. Okay, and mathematically, here is the notation where phi is the function, the class that we are interested in, and then chi is the data points, and this is defined to be the middle part, where Z is the Radmacher distribution, which takes 1 and -1 with equal probability. So it is 50% probability to be 1 and 50% probability to be -1. Okay, and we are requiring this complexity to be upper bounded by something which is of order 1 over n. So this is the most important assumption, I would say, in this definition. And from here, you will be you are already seeing that this is not this class is not the same as the Lipschitz function. So if here phi were the Lipschitz function class, then on the right hand side you will have an upper bound which is of order n to the negative CD, where D is the dimensionality and then C is some constant. Okay. And from this definition, we are requiring something to be smaller than the class of one Lipschitz function. Okay. One very quick example for this empirical Radmacher complexity. If I take phi to be a linear function, where the function is defined to be the inner product with some weights, and the norm of the weights is less than or equal to 1, then this Radmacher complexity is upper bounded by the maximum of the L2 norm of all the observed data there, divided by n. So then after giving this definition, the first question would be, since we call it to be the generalized maximum mean discrepancy, is it really generalizing the MMD that was defined in the literature? So the answer is, of course, yes, under some assumptions. So by prescribing some K1, K2 constant on this reproducing kernel K, then we're able to say that this Hilbert space with norm unit ball can be chosen as the task function class for the GMMD if I identify A1 to be K1, A2 to be K2, etc. Where A1, recall A1 is the Lipschitz condition for the task function class, and then A2 is the function evaluated at 0, the upper bound of the function evaluated at 0 here, and then A3 is the constant related to the Radmacher complexity. Okay. Any question? Okay.
Maybe, sorry, one quick question. So here you are showing that, okay, that the previous class is I mean, you can recover the previous class using the generalized notion. Do you know, is there like other elements? I mean, if it is generalizing in the sense you also include other
yes,
elements that were not covered previously.
You mean other like test function class that can also be used?
Right, yeah.
Yes, we will discuss later, like here.
Okay.
Yeah, like in
okay, thanks.
more slides. Yeah.
Nice, thank you.
Okay. Okay, so but before talking about that, let me show the first results in our paper, which is some property for this GMMD. So the first part is sort of trivial. It says it gives the upper bound or the relation between the GMMD and then the Wasserstein metric. So here is simply by the Lipschitz coefficients of the function, test function class. And then the second part is by the inequality between the Wasserstein metric. Okay. But what can we say about the distance between the targeting distribution and the empirical measure? If we are measuring using the GMMD, then on expectation, we are able to show this is of order 1 over n. And then we can also give the upper bound in of the second moment, okay, which is of order 1 over n. So from the first inequality to the second one, this is basically you are computing the variance for this random distance, and then this part is exactly the first term in the second line here is exactly the variance. Okay, and then moreover, if we if mu satisfies this transportation cost inequality, then we can also give a upper bound in high probability. Let's say in this way. So we know that the distribution, the distance in expectation is upper bounded by this right-hand side. And then if we subtract this 1 over square root of n term, and then this probability is exponentially small. Okay, and then one special example for this T1 inequality, this is the transformation cost inequality, is when mu is the sub-Gaussian distribution. So sub-Gaussian distribution is a class of distribution where the tail is lighter or equivalent to a Gaussian distribution. So basically, you can control the tail distribution by a function which is e to the minus ct square, where t is the tail. So if the distribution, the target distribution has that property, then you can also give this distance in a high probability bound. Okay, and then a sketch of the proof. I think due to the time limit, let me skip this part. But basically, we are using the definition of this empirical Riemann complexity. The distance, this random distance between the targeting distribution and the empirical measure can be, first of all, this is the defined by definition. We can write it in this way, and this can always be upper bounded by twice of the Riemann complexity. Okay, and then we give the upper bound in expectation. For the upper bound in variance, then the very useful inequality is this F-Stein inequality, which can give which is used for variance for any general function of random variables, where basically you are replacing a random variable xi by yi, which has the same distribution, and then that provides an upper bound. Okay, and then for part C, by defining some Lipschitz functions, then we can use the results in the paper by Dulac and Ruimeng in 2020, and then to produce these high probability results. Okay, and now to answer Matthew's question, yes, there are indeed other examples for this testing function class. The first one would be the two-layer neural network, or the function space that is related to the two-layer neural network. So we know that two-layer neural network can be expressed in this. So you have the affine transformation for the hidden layer, and then activation function, which is denoted by sigma. And then there's another weighted average or affine transformation. So in this particular formulation, there's no activation function for the output layer, right? So considering a two-layer neural network parameterized in this way, and then putting some assumptions on the weighted and bias, then taking the limit as the hidden neuron goes, the number of the hidden neuron goes to infinity, and this is the so-called barren space. Okay, so we're able to show that the barren space can also serve as another example for a testing class, and I would comment that here the sigma is chosen to be the ReLU function, and we are trying to generalize to other activation function, but at the moment we haven't been successful in that direction, and the reason that it is successful in ReLU is it has a lot of symmetry here. So the analysis for giving some upper bound indeed using those symmetry a lot. Okay. And more generalized, we can the multi-layer fully connected neural networks also provides a space which can be used at the test function class. This is called a generalized barren space. So basically you are building on top of the barren space and then to have more and more layers. Okay. And then another one that we also consider in the paper is the residual neural networks, which we know the difference between the output of the I+1 layer and the ith layer is usually modeled by some functions of the ith layer input. So in the limit as the depth of the layer goes to infinity, and then if we are doing the rescaling, then this can be viewed as a ordinary differential equation, right? So then this will induce produce the flow-induced function space. Okay, and all those three spaces satisfy our three criterion for this phi, of course, under some assumptions of their coefficients. Okay. And if I have time, I have some backup slides to show more details. But now let me talk about another thing here. So the previous results shows that if we take another testing function class, then we are able to show the empirical measure converge to the targeting distribution in the GMMD sense, and then is free of the cursive of dimensionality, right? So then the question is, given that we have something that is close to the target distribution in GMMD, can we construct something on top of it that is close to targeting distribution, but is under the Wasserstein metric? Okay, and then for this particular type of models, the answer is yes, and this is called the bias potential model. How this class of model is constructed. So let me talk about definition here. So we need to have a known base distribution P. And then this class of distribution is constructed using the test functions V in the phi. So first of all, we need the integrability of e to the minus v here, so that we can define a proper distribution by the Radon-Nikodym derivative. You want to do a rescaling here such that this is a real probability. Okay. And then we have the following theorem says, if the target distribution can V star, mu can be expressed by the a function in the testing function class phi, that means if my mu can be expressed by this Radon-Nikodym derivative of the V star, okay? And nu is something that we already know that is close to our targeting distribution under the GMMD sense. Okay. Then by the following construction, we are able to say that the distance between the targeting distribution and our new constructed distribution under the Wasserstein metric can be controlled by the targeting distribution and the already known distribution under the GMMD sense. And then this upper bound is both in the one Wasserstein metric and the two Wasserstein metric. Okay. So the way to construct it is the following. We define a loss function using the information of this nu, which we already know that is close to the targeting distribution under GMMD. Okay, so nu is explicitly using here. And then we are minimizing this loss function. And then we call the minimizer to be V prime. And then we use this V prime to produce the nu prime. And by the spatial structure of this nu prime, then we can achieve what we want.
So, sorry, can I ask you a quick question?
Mm-hmm.
Thank you. So here is this nu could be, so mu could be the target distribution and nu could be an empirical distribution with endpoints so that you get,
enough.
Right, they are close enough in your generalized way of measuring the distance.
Yes.
And then you solve the then you try to solve the optimization problem, finding a function v that minimizes the loss.
Mm-hmm.
And from here you deduce a new distribution, nu prime. Okay.
Yes, exactly. Yeah.
Exactly. And this optimization problem, is it in general solvable, or how do you find the?
You mean numerically? That's a good question.
Okay.
Yeah, we concerned about the theoretically, yes, but
okay, sounds good.
Or I mean, even theoretically in the paper we discussed, here could be the arc infimum, and then the V prime. It is possible that V prime is not attainable. Yeah.
Okay, I see.
And
I see. Okay.
Yeah, you will have an epsilon term everywhere in the in your upper bound, basically.
I see. So you can do some approximation and it still works. Okay, I see. Thank you.
Yeah. Mm-hmm. And then the good point here is that the GMMD distance between mu and nu is free of the dimensionality. So that means the upper bound of this Wasserstein metric, the Wasserstein distance, is also free of the dimensionality, right?
I see. I see. Yeah. Thank you.
No problem. And then, of course, I need to mention the assumption here. The known base distribution also needs to satisfy this T1 inequality, this so-called transformation cost information inequality. Okay. And then if moreover the known base distribution satisfies this log Sobolev inequality, a stronger one, then we can bound the two Wasserstein metric by a stronger upper bound. I mean, a smaller upper bound, which means stronger. Because we in our mind, the GMMD this distance is always smaller than 1, then the square root would be smaller than the fourth root of it. Okay. And then another application for this GMMD is when we are measuring the epsilon Nash equilibrium from the Midfield approximation. So I know this is the Midfield game seminar, so let me be quick on how the Midfield game is developed from the n-player game. So basically, you have a symmetric n-player game, and then every player or agent is interacting only with respect to the empirical distribution of everyone in the population, and then everyone is trying to minimize his running cost plus some terminal cost. Then if n is large enough, then we naturally go for the Midfield approximation, where you are minimizing this equation 1, and mu is some mu t is some measures, a flow of measures to be determined subject to some stochastic differential equations that describing this x. Okay. And then the solution for the Midfield game is defined to be a fixed point of this problem, such that for a given flow of measure mu, if I'm solving the problem 1, then the law of the optimal states would be consistent with the given flow of measure. Okay, And then if we are able to find this mu, then using the midfield control alpha, that we are able to construct a epsilon Nash equilibrium. So the approach here is discussed in a paper by René Carmona and his co-authors de la Rue in 2013. And so this very classical, very well-known results. And here, what we want to show is, of course, for those epsilon Nash equilibrium approximation, there are some assumptions on the model parameters for FG and B and sigma, and in particular, there are some Lipschitz conditions of these measures. Okay, and in the original paper, all the Lipschitz criterion are imposed using the two Gaussian metrics. So here we are replacing those assumptions by the GMMD, the one that we are proposing in our paper, and then basically we are having a stronger assumption, or we are measuring the continuity, the regularity of this measure using another metric, and this metric is stronger than the Gaussian metric. And then the gain here is that our epsilon Nash equilibrium, this epsilon would be free of the dimensionality. Okay, so this is the improvement that we can have here. Okay. So if for their original results, for the epsilon Nash equilibrium that they are constructing, where n is the number of the player in the game, there's a clear dependence on the dimensionality of the state space, the dimensionality of X, which appears here. And this is exactly introduced by using the two-bar system metric. Remember the two upper bound that related to the COD that I present like in the first or second slides today, they exactly have some upper bound of this order. Okay, but for us, because we are measuring this regularity in a different way, then we have a upper bound where we have the epsilon Nash equilibrium, where this epsilon is only in the 1 over root of n order. Okay, and then the first several equations are the standard probabilistic approach of analyzing a midfield game using forward-backward stochastic differential equations. Basically, for solve this fixed point problem in midfield game that can be translated into solving a system of forward X and then backward Y stochastic differential equations, where H is the usual Hamiltonian of the system. And then once we identify this solution here, and assume that there's a decoupling field, where that means we can write Y to be a function of T and XT, then we are able to construct a solution. Construct some measures. To construct some strategies using the solution of this FBSD system and the minimizer of the Hamiltonian, which is the alpha hat here. Okay, and then assuming if everyone is using this strategy that is constructed from the solution of the midfield game, then the epsilon Nash equilibrium is obtained, and with this order of error. Okay. So this is pretty much I want to talk about for the first part. How much time do I have, Matthew?
I think you can, because we started late. So I mean, I think if you want to take 20 minutes or
okay,
something like this. I don't know how much time do you need.
I can adjust. Yeah.
Okay. Okay. I mean, we can go and we can see. I think we can finish a bit after the scheduled time, because we started a bit later. So
okay, cool.
Just take your time. Yeah.
Thank you. And actually, for this definition, we also have a version which takes care of the convergence of distribution for processes. So here we are focusing on if the distribution is on the RD space. But in the paper, we also have a version of analysis where the distribution is on the continuous process on RD space. And then in that version, we're able to show the convergence of, this propagation of chaos, or this the convergence from the n-particle system to the Markov loss of stochastic differential equation is free of the curse of dimensionality. Okay, but due to the time limit, I didn't include that part in the talk, but I have some backup slides here. Okay, so now let me talk about the second one, which is a deep learning algorithm for midfield game with common noise. That was a paper I did with a student I'm supervising at UCSB, and then that was accepted last year in the SML. So basically, in the problem we want to solve is a midfield game with common noise. So the additional term here we are adding is some Brownian motion term, which will appear into every agent's dynamics if we are viewing it from a n-player game perspective, or in the midfield regime. We would call this W to be the individual noise, and then for this representative agent X, and then the B is the common noise that is appearing into every agent. Okay. And then the solution for the midfield game with common noise is still a fixed point problem, but now for the coincidence between some given flow of measures and the law of some optimal path, we need to take into account this common noise. So we know that for individual noise, if we are keeping propagating, or if we are keeping averaging for all the population, they will average out, right? But for the common noise, they will exist there. And then that's why in this consistency condition, we need to take into the common noise into account, and then we are requiring the given flow of measure to be coincide with the conditional law of the optimal path following the given flow of measure. Okay, so this is the only difference from the previous 6-point problem that I mentioned. Okay, and then later on we will introduce a concept called signature, which can efficiently represent this conditional law or the conditional moments. That is what we were able to solve in that paper using this signature, basically. Okay, but before talking about our algorithm, let me briefly mention the 3 ways to deal with midfield game with common noise. Theoretically. So there is a recently developed approach which is called the master equation. Basically, this is a second order Hamilton-Jacobi-Bellman equation that involves derivatives with respect to probability measures. So if we are trying to do some numerics for a master equation, then that involves discretizing the probability measures, okay? Which is not easy task, not an easy task. And then the second one is we can also reformulate it into a stochastic forward Fock-Planck and AJB system. So for classical midfield game without common noise, then the one way to describe the system is you have AJB equation which characterize the optimality of your control, and then for a Fock-Planck equation which characterize the dynamics of the whole population. Right, and now with the common noise, you have the additional BT term there, and this will make both the Fock-Planck and the AJB equation to be stochastic, and then this give us a forward-backward coupling stochastic partial differential equation. Okay, and a third way is the probabilistic approach, which was actually shown in the first part. This is to translate it into a forward-backward stochastic differential equation of the McKim-Vlasov type. But for this to work, we always require the convexity of the Hamiltonian or the concavity of the Hamiltonian, depending on whether we are doing minimization problem or maximization problem. Okay, so without this structure of the Hamiltonian, then this is not a possibility, right? Okay, so what we are doing in our paper, so we are not using any reformulation here. We simply do a direct parameterization. This is in the spirit of a paper by Ruimeng Hu and Gaussian Kernel in 2016, a very, I would say, old paper, like 6 years ago. And to directly parameterize the control and then to minimize the loss, which is the discretized version of the objective in the Midfield game. And then we are using the signature to represent the conditional Midfield, which we propagate from time to time. Okay. So now let's talk about 3 ingredients in our methodology. So the first one, as I mentioned, this is a deep learning. So we are using neural networks to parameterize the alpha. Okay, and then this is the reference. I believe that was the workshop paper in NeuralIPS. And then since this is a fixed point problem, it has been evident in both in the theory and also in practice. I know for some of the audience here, you guys are also using the fictitious display to solve the Midfield game. So I'm using the same approach. So basically, give for the one is you start with a given flow of measure, solve the problem, and update the flow of measure using some averaging of all the path distribution, and then keep going on until they reach equilibrium. Okay, so this is also the way in our machine learning algorithm. And then the third part is what we add here to deal with common noise. So when update from mu_n to mu_n+1, we are using the signature to express this conditional law or the conditional moments that we are targeting here. Okay, so what is a signature? So this is a concept in the rough path theory. Basically, a signature of a process is usually denoted by S of x, and this is an infinite dimensional object. And the case object is a iterated integral here. And usually, since this is an infinite dimensional long thing, in practice, in numerics, we do a truncation of this vector. So this is called the truncated signature of x of depth m, and the notation is here. And for this truncation, it will have this many terms because x is of the dimension Rd, right? So if you are interested in the rough path theory and in particular in signature, then this is a very good reference by Lyons. And I do observe they have many papers on using signature, using rough path theory in machine learning. Okay. So why are we using signature here is because it has a very good property. It can characterize this path, the x, like unique up to the tree-like equivalence. And if one argument, one component, or one dimension of x is strictly increasing, then it is unique. So there's no up to tree-like equivalence. And then the trick here is we are adding one dimension to the process that we are trying to approximate, or that we are adding one dimension t to the process that we are interested in. So instead of working with x, which is our something that of our interest, we are gonna to work with x hat, which is the augmented version between t and xt. So then the first component, the first dimension is strictly increasing. Then there is a one-to-one correspondence between the process itself, the path itself, and then the signature of the path. Okay, and then in our algorithm, this path of our interest is the Brownian motion, the common noise. So we know that for the nth term conditional law would be defined in this way. And by the equivalence between the pass and the signature, we can say we replace this condition, or this is intuitively, this means we are doing a prediction of the law of the optimal trajectory given the Brownian common noise path. Okay, and then this is equivalent to say that we are doing the prediction given the signature of the common noise. Okay, and from here to here, from the middle term to the last term, this is approximation because we are dropping the terms after depth m. So we are only doing prediction with the first mth term, and this approximation is valid. It's a valid choice because for signature there's a good property which is called the factorial decay. So factorial decay says that for this infinite long object, if I'm only truncating for the first m terms here, then all the rest will only contain information up to 1 over m factorial. Okay, so for m sufficiently large, then all the tail terms will not have many information. Okay, that's why this is a we didn't include those, and then we have some truncated signature as an approximation. Okay. Time. Okay. So this is like the flow chart of this algorithm. Suppose that at the moment you already know some given flow of measures we denote by mu hat n-1 from the n-1 iteration. And then for this nth stage of the fictitious play, you simulate all the Brownian motions, the individual noise, the common noise, and the initial points, and then we can do this optimization problem. This is a classical optimization problem. And then once this is solved, we can produce the optimal trajectory at the nth iteration. Okay. And then meanwhile, we can also calculate the truncated signature of all the common noise, the augmented common noise for this one-to-one equivalence. And then for predicting or for predicting the conditional moments given the common noise, we are using the a linear regression to get the coefficient L. So this is approximately my a linear inner product or a linear regression of the function on x on the truncated signature. And then once we obtain this L, these coefficients, then averaging the past of the conditional law means we are averaging past of the this linear coefficients. So that's very convenient. You are not you do not need to remember all the neural networks. You only need to remember the last average of the past, and then do a weighted average with the current estimation L, and that gives you the L bar. And then for the L bar, this is there's an equivalent way to predict the conditional law for any unseen common noise, and this will be the given point for the next iteration of fictitious play. Okay. So let me justify the orange block here. So why we can do that? So for moment iteration, basically we are predicting the iota of a x given the filtration of the common noise, and then we can view this as a map from T and the Brownian motion path. Then we're able to show that there exists for any epsilon, there exists a linear function of L such that the map, the distance between the map and this linear functional is as close as we want. And then in the practice, we approximate this linear functional L by a linear regression on this iota of X on the truncated signature. And then the reason that we are using linear regression is because this is considered to be the best linear prediction of iota on the truncated signature, right? Okay. And then some of the advantages I've already mentioned for having this Ln, which is the coefficient from the linear regression at the else iteration. So first of all, if you have unseen common noise, omega tilde, then how to produce it using using Ln? This is simply a linear product. And then the second one I also mentioned, if I have L1, L2 until Ln from every stage of the fixed display, then for averaging past, I'm averaging only the L term. So this is by the linearity of this approximation maps. Okay. So that's pretty much I want to say about the algorithm. We have some numerical example. In that paper, we carefully choose 3 example in Midfield game with common noise, and they all have benchmark solutions, and then we do some comparison. And in particular for this example, this is a utility maximization problem. So agents are concerned about maximizing the utility of some terminal wells plus some intermediate assumptions, consumptions, but both are compared to their peers. So my happiness is not only measured by how much I consume, it's also measured by how much more I consume than my peers. Okay, and this is one way to construct Midfield games. And then gamma t and mt, these are the Midfield terms that involves the this conditional law here. And then our numerics shows that so basically for every plot there are solid lines and then the dashed lines. Maybe you can see here, this is the solid lines and then this is the dashed lines, and 3 different colors means 3 independent trajectories of the common noise. Okay, so we can efficiently solve the problem for not only for one common noise, but for every like common noise, I would say. I know that for classical for in the past for Midfield game, for numerical algorithm of Midfield game with common noise, the approach is usually you fix the common noise path and then you solve the whole problem, right? And then you have another common noise path and then you solve the problem again. But here we can solve all those simultaneously. It's like a cross-sectional regression methodology, I would say. Okay, so I think let me stop here. I don't want to take too much time from you guys. And then here's a quick summary. We are trying to apply the GMMD in other contexts, and we are still looking for other interesting problems. So I would be I would appreciate if you can have if you have some comments on where this GMMD can be used in other problems. And then another goal is we are trying to see if there are similar results can be derived for the GANs, not only for the bias potential model. For the bias potential model, it's a class of very nice, but not very widely used model in applications. We hope that similar results can be also developed for GAN. And then the third thing is we try to extend this signature deep fixed display approach beyond the conditional moments interactions. So what if the interaction is really through the whole distribution, or it is through the local density, and then how can we approximate efficiently using the signature object? Okay, so thank you so much for the attention, and yeah, any questions?
Thank you very much for the very nice talk, Ruimeng. Other questions or? Okay, maybe I have a question related to the fictitious play. So maybe your diagram. So here for this part in orange, so just to check if I understand correctly, the average from fictitious play is in the, let's say, the green box. Is it correct? This is the 1/n here? Okay.
Yes.
And do you expect this? So this works because, is it because you have a linear relationship thanks to the moments, or where, okay, this is the main difficulty to extend beyond the moments, or what are the main difficulties if you want to extend that to interaction through more complicated?
So first of all, if we are having a general distribution interaction, I don't know how to use something like this to express. So here,
yes.
we can do linear regression and then give a linear maps, right, from the signature to the objects that we want to approximate. And then for general distribution, I don't know how this can be worked out. And then the second question is, yes, even there could be some approximation scheme or approximation regime, then is there still linear, and then can we still do this average very in an efficient way? Yeah. So let me know if you have ideas, on this part. Yeah.
Okay, I see. Yeah, thank you.